In this activity, I want you to take this simple closed loop system and use it as a motivation for a more formal discussion of closed loop tracking. So we've already seen the example through the spring mass damper, and now what I want you to do is essentially continue that. So what we've done is we've looked at the proportional controllers and proportional integral controllers for a reference step. So we've kind of done 1 and 3 here for a different system. So now I want you to do it for this particular system. And then I also want you to consider what happens when the reference, that capital R input, is a ramp instead of a step. And so that's what you're going to do in what I'm calling 2 and 4. So what I want you to do is I want you to essentially look at this system and analyze this system and understand what that steady state tracking error is for all of these different scenarios. So these two, proportional and PI, essentially tell you what K of S is. And these here tell you what R is. And what I want you to do is characterize that steady state tracking error in these 4 different scenarios. So go ahead and take a few minutes, look back at the last couple activities with that spring mass damper if you get stuck, and then I'll go through my solution. All right, so we're first going to take a look at what happens in the case of proportional control. So when we're using proportional control, then I'm just going to call the controller gain K. We could call it KP, but let's just call it K for simplicity. So when I do that, I'm going to compose the tracking error transfer function. And so this looks just like what we did when we did that generic transfer function. So I could actually go ahead and pull out that tracking error. So it's transfer function, which is just 1 over 1 plus GK. So that's a little bit of a shortcut. You just need to make sure that this transfer function and the block diagram looks just like what we had before. And so that's why we're able to just pull this. You could certainly go through the closed loop algebra in order to get to this point as well. So if we take this as our starting point, then we go ahead and plug in G and K. So G is just this value, and K is just a K constant. I'm going to multiply top and bottom by this S plus 10 to yield this as my closed loop transfer function from the reference to the tracking error E. And so now what we're going to do is we're going to use that final value theorem in order to analyze 2 different scenarios. So when we have a step function, then the reference over here is 1 over S. And so that means that I'm going to evaluate the steady state tracking error as the limit as S goes to 0 of that S term multiplied by what E is. And E in this case is this closed loop transfer function multiplied by the reference 1 over S. And again, in that step function case, it's super nice that these two cancel. And now we're just evaluating what happens when S goes to 0 of what's left. And so that means that this term would go to 0, and this term would go to 0, leaving you just essentially 10 over 10 plus 100k, or if you divide by 10, then you get 1 over 1 plus 10k. And so what this is saying is that k is just going to be a number, and so that means that the tracking error in steady state will be some number, and if k is, 4, say, then this would be 1 over 41, which is a relatively small number, and it's going to get smaller the bigger we make k. And so this is very similar to the scenario that we saw before. And so the way that we can make this smaller is simply by making k bigger. And so the statement that we'll make is that proportional control on this system here can track a step. So we say that it can track a step, but that it has a constant error. And so that's the terminology that we'll start to use now. Well, we see that if we now increase the complexity of the reference to 1 over S squared being corresponding to a ramp, then essentially the math you'll see is exactly the same between these two cases. The only difference is that this is a 1 over S squared for the reference. And so we cancel out one term here and one term here, but that this s, we have one factor of s that stays here. And so that gives us essentially, as s goes to 0, this term goes to 0, this term goes to 0, and this term also goes to 0. And so this is going to be 10 over 0 essentially as this goes to 0. So that means that as this goes to 0, the whole quantity blows up, and so that's why it goes to infinity. And so what this is telling us is that the steady state error as time goes to infinity means that the tracking error goes to infinity. So you're never actually going to go time to infinity, but what this is telling you is that the tracking error is blowing up. It's getting bigger and bigger and bigger, and if you were to go off to get the true steady state value, it would go off to infinity. And so the way that we kind of call this or describe this is that that proportional control on this particular system cannot track a ramp. So in this case, it was able to track a ramp with a constant error. Here, because this tracking error blows up, we say that proportional control is not able to track that ramp. So now we're going to move on to our integral control. So again, similar to what we did in the mass spring damper. We're going to use the same starting point here, but now our K is going to be both proportional control and integral control. And what I'm going to do is I'm going to put this S factor that comes from this term, specifically the integral term, I'm going to put it in green, and I'm going to leave that so you can see where it moves around as we simplify the transfer function. And that S being colored like that is going to connect with the next video that covers this in a more theoretical point of view. So it may be worth to come back to this slide and take a look at it after you've gone through that more theoretical derivation. So when we multiply both top and bottom of this transfer function by s plus 10 and a factor of s. And so that's why we have a factor of s and s plus 10. That's why we have s times s plus 10 here, and then we have essentially the rest of this numerator left right here. So this is our closed loop transfer function from the reference to the steady state or the tracking error. And so now what we're interested in understanding is what is that steady state tracking error when the reference is a step and when the reference is a ramp. So when the reference is a step, we plug in 1 over s for our reference. And again, this can cancel this. And what happens is now that s goes to 0, so this term goes to 0, this term goes to 0, and this is left. But in the numerator, this extra factor of s essentially makes the whole thing go to 0. And so you could multiply this out and get the same result, but you'll see that this extra factor of s that we have up here, this independent factor of s, is what is driving the whole numerator to 0 and what's creating a 0 steady state tracking error. And so it is the influence of that integral term, just like we saw in the spring mass damper, that forces the steady state tracking error to 0. And so that means that the way we'll call this is we'll say proportional integral control tracks a step with 0 steady state error. If we look at a ramp now, so one more thing to say about actually the step case is that if you look back at the step before, proportional control could only track it with a constant error. Now we can track it perfectly with 0 steady state tracking error. So the proportional integral does a better job, right? So now as we move to the ramp case, then we plug in 1 over s squared for the reference. And so now one factor of s cancels with this, and another factor of s cancels with that extra term in the numerator. And so now what happens is, as we take s goes to 0, this term goes to 0, this term goes to 0, this term goes to 0, and I'm left with 10 over 100k I, or just 1 over 10 ki. And so what this is saying is now that we've gone from a step up to a ramp, we can't track with zero steady state tracking error anymore. Now we track with a finite error, and it goes like 1 over 10 ki. And this requires a high ki gain value in order to make this error small. And so again, we're using that high gain, but we're using high gain to achieve tracking of a ramp, a faster signal than a constant signal. And so the way that we'll call this again is the fact that proportional interval control can track a ramp with constant steady state error. And so you can imagine that tracking a ramp is harder than tracking a step. And so you can observe the pattern that we're seeing here is that the integral control helps you achieve better tracking and kind of moves you up in terms of the type of reference that you can track. And so what we're going to do in the next video is to kind of formalize this in a more abstract and theoretical framework in terms of tracking different factors of 1 over s to the n. And so in this case, n is 0, and in this case, n is 2, or sorry, in this case, n is 1, and in this case, n is 2. And so now we're going to see as you can kind of extend this to arbitrarily high polynomials, which the Laplace transform goes like this. So that's what we're going to do next, and we're going to use this set of examples as motivation.